Bismillahirrahmanirrahim. Ladies and gentlemen, Assalamu alaikum. In the previous lecture, we went away from the regression, but in this lecture, we will be converging again towards regression. From this lecture and to the further many other lectures, we will be talking about the multivariate regression model. Most of our courses comprises on the multivariate regression model because the simple or bivariate regression model is only the simplest way, and most of the time we are using the multiple regression model. In the previous lecture, if you remember, we talked about the hypothesis testing. That is a very important concept, because if everything is okay, we have analyzed the data, but still we are unable to see that whether our parameters that are our estimates now are significant or not significant. To test their significance, we get help from the hypothesis testing. Hypothesis testing is a very interesting technique of the statistics. So in hypothesis, what we learned about, we just saw that how much our estimates are how much compatible to the stated hypothesis. Compatible here means how close. What we want that our estimates should be very, very close to our hypothesis statement. After this, we study two kinds of this: the interval, the confidence interval technique, and the test of significance. I need not to give a detail, but I would like just go through from this, that in the confidence interval technique, we talked about two-tailed and one-tailed test. Simply, we make an confidence interval and then see that whether our estimate has the probability to fall in this, and we then say if it falls in the acceptance region, we say that we are unable to reject our null hypothesis. But if it falls in the critical regions, I am talking about the two-tailed, if it finds in the tail side, we say that we can reject our null hypothesis. Then there was one-tailed test on the similar basis and footing, and then we talked about two types of error, type 1 error and type error. I am sure you are aware of this. The most important in the previous lecture was that how to form the null hypothesis. Interestingly, the major drawback of the statistic is that the level of significance, its choice is very critical. But fortunately and very interestingly, if we set the level of significance, then there is only manipulation, and the method becomes only mechanism, and we can immediately build a confidence interval. So the process is that how to form the null and the alternate hypothesis. Alternate hypothesis also called the maintained hypothesis. We test our null hypothesis against the alternate hypothesis. So the interesting and the more you can see the critical situation is that how to form the null and the alternate hypothesis. We studied no rule of thumb, but still the prior expectation, the previous knowledge, the prior history, it helps us, or the prior theory or the theoretical background, help the researcher to make null hypothesis and the alternate hypothesis. The most interesting and the noticeable thing is that the null and the alternate hypothesis should at any cost be formulated before you start before your analysis, because if at the end of your analysis you form the null hypothesis, there is the probability that you are going to bias towards your required results, because now results are before you and you can make a null and alternate hypothesis that can help you, that can verify your statistics. Then we talked about very shortly about the p-values. P-value is you can say the indirect way to say the t-statistics. T-statistics means we have to compare it with the t-calculated and the t-tabulated, but looking at the p-value, that is also called the exact level of significance. What we say that we see the probability of obtaining a obtaining t statistics greater than or equal to the obtained. And if according to this, and there is a negative relationship between the t value and the p value. As the t value increases, p value decreases, and you can say in the conventional or the traditional way, we want that our p value is less than 10%. It is not still a benchmark, but most of the time researchers are confining themselves onto these three steps: 1%, 5%, and 10% level of significance. But the most important in this is let the researcher decide how at which level he reject or accept. If your study is not too sensitive, you can go up to 15% rejection level or 20%. But at the same time, if your study is extremely sensitive, like life-saving drugs, you will have to restrict yourself at 5% or 1%. So what we are going to cover today, we will see another kind of regression, that is regression through the origin. In the previous lecture, by now, what we talked about, that we have the regression that has two parts. The one was the intercept and the other was the slope. In this regression, we are just leaving the previous one, and we are saying that there is no intercept and the regression runs through the origin. We will see its benefit, you can say its problems, and what at the end we will come to know some of the substantial results, that in which cases we should use or we should avoid it forever. Then after this, we will touch the topic of units of scale. You know, there are different units. For example, if I take the taxes, one person may take the taxes in million, the other may use the billion. Similarly, if you are taking a variable that is the distance, you take it in kilometers, the other take it in meter, and the third person also take it in the centimeter. So it means there is measure of scale. We will be talking about that if there is change, if one researcher to other researcher change in the scale, although the practical meaning will remain the same, but its interpretation and some of its statistics will change, and we will have to keep a critical eye on that. And we will see that there is interesting relationship that without going into detail, we can just have the indirect method, and we can guess that what is the value of this if we take that kind of scale or that kind of scale. And if the time permits today, after this lecture, I am going to introduce the E-views. So it is a time to fulfill my promise that we are going to learn the E-views, and I hope that you will immediately start install the E-views on your laptops, because if you are unable to catch this, I think you will be unable to do the assignments, and particularly the midterm or in the final exam. You may have a good command at least on the basic functions of this E-views. So starting from this, a regression through the origin. Sometimes, not most of the time, but I am saying that sometimes the theory to which we are studying, it states that there is the situation that there is no intercept. What this means, that the now relationship between the dependent and the independent variable has become proportional or direct. There is no link, and if both are increasing or decreasing in a proportional way. So if I write this here, that this is our function, population function. The previous one was beta 1 xi plus beta 2 x2 plus ui. This beta 1, only there was beta 1. So what was this? If you remember, I would like to write here that this is the population regression function, the previous one, the traditional, about which we kept on talking up till now. Now I am just going a bit further from the previous concept, and I am eliminating or dropping the intercept from the regression model. So this is the regression model, that is the population regression function. Beta 1 plus beta 2 x2. And if you see it on the diagram, it is very interesting that this is the situation, this is your x variable and this is y variable. So this is the slope of this curve is, this is the beta 2, and you know beta 2 hat is equal to delta y over delta x, change in y with respect to x. So here is intercept, that is called the beta 1. So this is up till now we were concerned about this, but now what I am saying that we have some prior information and we say no, there is no intercept and the situation is beta x2 plus ui. I can write also ui here. So what is this? What this says that now the relationship between this variable, that is your only independent variable, and your dependent variable has become proportional. One-to-one relationship there. So what will happen on your right hand side, this one, if you make this is the x, this is y, and now your regression will run through the origin. So this is the situation, and now you can see that now beta 1 is equal to 0, no intercept there, and this slope again showing that this is change in y as I take it to the vertical axis, and this is change in x, and beta 2 is equal to change in y with respect to x. So this is the situation when the regression is through the origin. For example, what is the simplest example, that you are the project managers and you know the cost analysis theory. What the cost analysis theory? If you know that there are two kinds of cost, that total cost is equal to fixed cost plus variable cost. What the cost theory says, that there is a exact relationship between the number of units of production and the variable cost, this cost. What this means, that this will remain same whether you produce only one unit or you produce more unit. This will fixed cost will remain, for example, your factory or your machines. What is the variable cost? For example, if you are making 10 units, I suppose your variable cost is 100. And if you will increase, you will produce 15 units, this cost may become 160. So this is the situation. The cost theory says now that there is a direct relationship, that as the number of units increase, the number of the cost also increases. Another interesting theory nowadays, you are talking about, listening about the functions of the state bank, and there is a very interesting theory that is called the quantitative theory of money, and I would like to just give, and what is the relationship? Look at this. Most of the time now in this government you listened about that the government is printing more notes. And what was the result? The result was immediately that the prices were rising and rising over time, and in other words you can say the inflation was rising. So if I say this is the price, this is the money supply. What this says, for example, if in Pakistan the money supply is 10 trillion rupees at this time, and I say the average prices are 10 in a specific market. So if this goes to 20 double trillion, the theory says that there is exact relationship at the, and this should also go to 20. So in this, if this is the situation, then the regression runs through the origin. It has no intercept, and we call this that this is the regression through the origin. Diagram and formulas in this case, when the regression is through the origin, the formula changes, and you will have to be well aware of this. If you look at this, that this is the without intercept about which we are talking now today. This is the beta 2 hat is equal to summation xi yi over summation xi square, and if you look at this formula, this was the previous one, and I am dead sure that you know this, that what is the this. The difference between the two formulas, look at carefully that in the traditional beta 2 hat or the beta 2 hat obtained from OLS in which the intercept was present, you can see the xi and yi in small notation, but at the left hand side you can say that its mission xi and yi are in a capital. So in a small, I would like to just give that if xi is small, it is simply that this is xi minus x bar, the deviation from the value from its mean. So the first difference is that the beta 2 hat formula becomes different in two of the cases. You should be very smart and you should be very wise while using the calculating the beta 2 hat, because if the function is giving in such a situation that the regression run through the origin, then you should use this kind of formula, but if there is intercept, you should go for this formula. Similarly, now comes to the variance of beta 2 hat. In this case, there is only a small difference between these two. The nominator is the same, no change in the nominator, but in the denominator there is a change, and the change is as was the previous. So what is the change? If you look at this xi, you can see that it is in a small notation, and this xi in variance of beta 2 hat, when the regression is touching the origin, then you can see the variance of beta 2 hat formula changes. I would like to again stress that be careful, be cautious, and concentrate, ponder, think about this before using any of the formula, because you may be confused that whether you should go for this formula or that formula. Simply speaking, when there is regression through the origin, the formula's notations are in the capital, and when there is traditional model, or you can say when there is the regression is with intercept, then there are small notation. And similarly, look at here, this is no change. So what is this? And the other thing is, now you can interestingly think that I did not take the beta 1 hat. I neither include the formula in this category of this, and I did not tell you the formula of this. I think you will be laughing on this, that what is sir saying? I am simply saying that beta 1 hat is not present now. We are not including the intercept because we are talking about regression through the origin. So when we have no intercept in one equation, we need not to worry about its formula because it doesn't exist. No formula exists for this. Two differences in formula. Again, go back and see the two differences. The first is raw sum of square. A raw sum of square means, when I said this is the capital, this is the raw sum of square. This is only, for example, this is x. This is x. It is 2, 5, and 9. It is simply x square is raw sum of square. This is 4, this is 25, and this is 81. So this is raw sum of square, but here in this sides there is the square sum of square, that is deviation from the mean. For example, this is small xi, and it is x minus x bar square. And if I take that this is small yi, it is simply yi minus y bar square. So first difference was that in the regression without intercept, we calculate the raw sum of square. In the other side, we take the deviation from the mean. The other is degree of freedom. Look at this. I deliberately did not explain this, that why this is n minus 1 and this is n minus 2. I am sure that you know that what is the difference between this, because when this is degree of freedom n minus 2. Why this is n minus 2? Because in this side we have two parameters. Regression is with intercept beta 1 and the regression is the beta with beta 2. So the degree of freedom is simply n minus k. K is the number of parameters to be estimated. So if it's n here, the number of parameters is 2, n minus 2 we have written. And if you look at here, this is n minus 1 because now beta 1 is not present in the model, and the degree of freedom changes. So two differences becomes in the formulas. The first is we take only the raw sum of square in this kind when the model is through the origin, and we on the other side we use sum of square that are the deviation from the mean, each value from its mean, and it is in the case of when intercept is present in the model. And the second is the degree of freedom. Very simple, that the degree of freedom in case of non-intercept or interceptless model, it is n-1 when there is bivariate regression model, and in the other case, the traditional, or you can say the classical case, this is the n-2. Now I would like to derive the formula. This is so simple as compared to your previous one. So because beta 1 and beta 2 are very important to derive the formula, you are lucky that beta 1 is not now present in the model, and we are only concerned about the derivation of the beta 2 at formula. I have written the formula this, it was also written here, and I have written here, so I am going to derive this formula. So I know that you are aware of this, that yi is equal to y hat, this is the explained portion, and this is the unexplained portion. So what is this? And you know yi is equal, it becomes yi is equal to beta 2 hat xi, now only one variable, one parameter, plus ui. This is the explained portion, and this is the unexplained portion. This is explained, and this is unexplained. And if I write that this is the r square, that is explained, you know, this is the measure of goodness of it, and this is also called the coefficient of determination. So I am just starting from here again, that what is this? Now ui, if you see that unexplained portion is the observed yi minus yi hat, and if I replace yi hat with ui hat is equal to yi minus beta 2 hat xi. So we have to start from here. The first we say that taking square on both sides, taking square on both sides, what it will become? It will become ui hat square, and this will become yi minus beta 2 hat xi whole square. Now applying summation on both sides, taking summation on both sides, taking summation on both sides. So what is this? If this will become, I would like to bifurcate it from here so that you can easily understand. So I was talking about that now we apply summation on both sides. So this side will become summation ui hat square is equal to summation yi minus beta 2 hat xi square. Now again, you know, I think you will not mind it that I go to the two basic conditions of the minimum, because we are interested in the values of the parameter beta 2 hat that minimize the residual sum of square. On the left hand side, if you see that there is residual sum of square, and we want to minimize this residual sum of square on the basis of the estimated beta 2 hat. So what we will be doing, we will be applying the first condition of the minimum, that is that the first derivative should be equal to 0, and we will be proving it by the sufficient condition that the second derivative should be greater than 0. So just starting taking first derivative, taking derivative, partial derivative with respect to beta 2 hat. So what will be this? Summation ui hat square partial beta 2 hat. Now it is equal to, you know, the power will come here, 2 summation yi minus beta 2 hat xi, and it is multiplied by this point is showing multiplication, and this is, we have to take again this derivative, and this is minus xi. And if I just multiply minus here with 2, it will become minus 2, and summation yi minus beta 2 hat xi into xi. Now minus is not with the xi, so what, now I multiply xi within the bracket, and this will become minus 2 summation xi yi minus beta 2 hat xi square. So this means now taking the second derivative. The second partial derivative should be greater than 0. If it is less than, our theory will be refuted here, and we will be calculating the maximum rather than the minimum. I am not going to the previous your discussion. So what is this? The partial derivative of ui hat square with respect to beta 2 hat square is equal to minus 2a is here. This is summation, and now there is no power, or you can say only one power, 1 minus 1, applying the power function rule. This will become minus xi square, and I can bring the minus outside the summation, minus, it will become 2 summation xi square, minus this minus multiplied by this minus, it will become positive 2xi square. Look at this, 2 is positive, and xi square can never be negative. So it is, and there are observation, so it is greater than 0. So we have proved this is the, you can say this is the sufficient condition. Sufficient condition. So what this, we have not still derived, but we have now proved that this is the minimum, and that what the first was the necessary condition, and you know in the necessary condition we put the first derivative equal to 0. So now this is in the refined form, first derivative, I would like it I would like to write it equal to 0. So we will write this equation on the next slide, that is minus 2, that the first derivative, that was minus 2 summation yi minus beta 2 hat xi square, and here is also xi yi, and it should be equal to 0. If you want to confirm this, it can be confirmed here. Xi yi, this is xi yi minus beta 2 xi square. Now we have almost achieved the target, and we are just going to manipulate this. It will give us the formulas of the beta 2 hat, and it should be equal to that we have taken first. So if I divide both sides by minus 2, dividing both sides by minus 2, so it will simply become summation xi yi minus beta 2 hat xi square is equal to 0. Applying summation now, applying summation, so it will become summation xi yi minus beta 2 hat summation xi square is equal to 0, and it will become that summation xi yi is equal to, we bring beta 2 hat term on that side, it becomes beta 2 hat summation xi square, and if I take beta 2 here, I bring that to that words summation xi yi over summation xi square. So this is the formula of beta 2 hat, This is xi square. So this is the formula for beta 2 hat. If you go look at this summation xi yi, and you can see this is the formula. So we have proved derived the formula for beta 2 hat. Now this was a just basic concept about the regression through the origin. Some notable features of regression through the origin. So this is very important, that it has some special features, so we should be aware of this, that what are its features. The more we are informant, the more we have grip and command and authority over the usage of this and the regression. Two special feature, it has two special feature, and the first is, if you remember before explaining the first, what we say, that the residual sum of square is equal to 0 in case of the regression that has intercept. That the residual sum is always equal to 0 when you run the regression that has an intercept in it. But this situation, that the residual sum, now look at the regression through the origin, residual sum of square is not necessarily equal to 0. This is important. So our big claim that we used to make in the previous and in the assumptions, now big claim is being hammered by this regression through the origin. Because regression through the origin, it hits the claim that was a very universal claim, that the residual sum of, and you know what is the residual, yi minus yi hat, the observed value minus the estimated value. There are some minus plus values above the regression line, there are minuses, and we saw that their sum is equal to 0. But here this you can say the universal claim is being refuted, and we are going against this. In the regression through the origin, the first fundamental property of this regression through the origin, or you can say the notable feature of this, is that when the regression through the origin, it is not necessarily true that residual sum is equal to 0, because now this has been estimated in a different way. But in case of the regression with intercept, the residual sum of square will be equal to 0. The second situation is that the coefficient of determination, I know you know what is this, that is the R square, or it explains that how much proportion has been explained by this model. So R square is also called the measure of goodness, or you can say the coefficient of determination. What this means, in when we talked about previously, we said that if you remember the one property of this coefficient of determination, we said that it is a non-negative quantity, non-negative value. But this claim is also refuted here, and we are going our own claim. But keep in mind, it is a non-negative quantity when the regression is with the intercept. I will again say that this is if yi hat is equal to beta 1 hat plus beta 2 hat xi plus ui hat. So now this is regression with the intercept. So in this case the expected value of ui hat is always equal to 0. So but in this case, for example, this is yi is equal to y hat beta 2 hat xi plus ui. Now it is expected, or summation ui hat is not necessarily equal to 0. So the second property, two property immediately and very quickly going through this, that when the regression through the origin is, that what we say, that residual sum of square is not equal to 0. And when the regression is through the origin, the coefficient of determination can be negative. The coefficient of determination can never be negative in case of you can say the traditional model or the model with intercept. So here look at this, I have highlighted this, that it may becomes negative when the regression is through the origin. Why this happen? Immediately the question arises, why this happen? The formulas of the R square has been derived in such a way that explicitly assume that intercept is present in the regression model. So when we built the formula on the assumption that it is explicitly included in the model, but we exclude it, then the formula that becomes, that is not a true representative representative of the conventional R square. Goodness of fit for interceptless model. So now what is this? This is, you can say, the regression without intercept. So what is this? It may not be appropriate. We just studied that now the formulas are different. So the traditional R square becomes questionable here, because when we calculate that the formula of that R square, we explicitly assume that the intercept is present in the regression model. But now we are saying that the regression is without intercept and it is running through the origin. So it immediately convinces us that we should go for some of the other formula. So in this case, it may not be appropriate through the origin. The R square or the measure of goodness is not appropriate for the regression that runs through the origin. So what is the solution? So we are never helpless and helpless. We have the solution. So what we calculate, we give another name to the R square and we call this is raw R square. That was in the previous, up to today discussion, our previous R square, that was the measure of goodness of fit or the coefficient of determination. What was that? Here we are assuming that this is the R square. And look at this, I have brought here formula for you. For the previous R square, it was summation yi and yi hat, and interestingly, here yi and yi hat are in the small notation. Look at here. Now you can see that it is in the here the sum of square or raw sum of square. So when the intercept is present, you should use this formula for the measure of goodness of fit. For example, if this is it tells us 80%, you will say that the 80% of the variation in your dependent variable are explained by your independent variable 1, 2, 3 or x many variable. But if you think that you have by chance deliberately excluded the intercept, that for the sake of objectivity and for the sake of, you can say, for the sake of accuracy, you should use this formula. It is not, the other thing is that now two R square, the R square, the raw R square and the traditional R square are not comparable. Why not comparable? You can immediately check that the formula for both this is now different. When the bases on which we derive the formula are not matching each other, their comparability becomes questionable. So we should be very careful about when we are comparing two R square. We can compare many R square if the regression is of the same type. For example, if regression is including intercept, if there are 1000 regression and 1000 R square, we can compare that. And the higher R square, we will say that it is explaining the major proportion of the dependent variable y. But interestingly, if one R square is the raw R square for the regression that has no intercept, and the other is the conventional or traditional R square, we are unable to compare this. So caution is, the first is avoid, very huge claim, avoid this kind of model unless strong prior information. Most of the time I will suggest and I will re-suggest that you should avoid such kind of model that has no intercept. Always use intercept because it gives more reliable result, and we will see that next, just after this, that what are the two major advantages of when we run the regression through with the intercept. So what is the suggestion? Avoid and be away from this, that you should always avoid when the regression is through the origin. You should not use this model, you should use the intercept. But however, if you have strong prior and the historical information, you can use such kind of situation and you can run the regression through the origin. What is the benefit of when we are always favoring and biased towards the model that has the intercept? What is the reason behind this? It has two reasons. The first is, look at this, if we have y is equal to yi hat is equal to 7 plus 0.6 x. So this is beta 2 hat and this is beta 1 hat. So what this tells us, now if you see that if this beta 1 hat is statistically insignificant, when statistically insignificant, it immediately means that indirectly it is equal to 0. So what will be if it is equal to 0, the regression automatically becomes through the origin. So we should include it that if it is significant, then it is good, and if sometimes it becomes insignificant, then automatically the regression is through the origin, and we should not be worried about this. The second is that if intercept is there, but we avoid it. Now look at the situation. If you remember the assumption of the classical linear regression model, and I think it was the number 9, the assumption number 9, what we assume that our model is correctly specified. So what we did, if there is, you can see, if intercept is present, if the theory says that the intercept is there, look at this, the intercept is there, but you exclude this, you are violating a major assumption of the classical linear regression, and when you will estimate by OLS, then there may be problem for this, and there are some other problem. So it is called the specification bias. So at the end of this slide, just one sentence, that avoid to run the regression through the origin, but at any cost. But if you think that there is some special, concrete, strong, solid reason behind this, then you go for this. Now I am going towards another topic, that is scaling and units of measurement. Before explaining this, I would like to just draw your attention that the scales and units of measurement change for the same data for the different researcher. For example, as I gave example in the beginning, if someone is interested in measuring the distance, and you are taking the same distance, one researcher is measuring the distance in kilometer, the other is using in the meter, the third is using in the centimeter. Similarly, if you are dealing with the weight, one is using tons, the other is using, you can say, the months, the other can say the kilometers, and the further other can also use the grams. So when this is the situation, how we should interpret the results, and what is one of the major example is that if our GDP is 2% comes, they take the GDP, one takes the GDP and taxes in million, the other takes in billion, then if they run the regression, in practicality there is no difference between the situation, because there is only change of measurement and scale. But we will see that interestingly some of the parameters and their definition will become a difference. So it makes the difference, and if the difference is there, then what is the sensible course? What is the sensible way to choose which kind of the measurement? For example, if you have the chance to select the GDP in billion as well as in the million, then what is the choice before you? There is no compulsion, and most of the time we avoid more zeros. It is just you can say the intuition, or you can say to hint towards this, that there is most of the time we should avoid many zeros. For example, if you are using million and there are 10 zeros, you can exclude 3 zeros by using it by billion, and further you can reduce the figure into trillion. When there are many figures, you can be easily, when you are using the higher, the billion and the trillion. Here is the example that I already explained. The result differ in both cases. Keep in mind the result differ in numerical values, but in practicality there is no difference. We will change our interpretation only. For example, just going further, for example, if you run if a person takes the measurement in 1 million, look at this, I would give example. This is the taxes, and it is beta 1 hat plus beta 2 hat GDP, gross domestic GDP. So what this means, what beta 2 hat, and I think that this is also GDP has been taken in million, and this is also in million. So what this conveys the message, this conveys the interpretation is that there is 1 million, 1 unit mean now 1 million increase in GDP. On average, there is beta 2 hat increase in taxes. And if I take the value of beta 2 hat, for example 0.75, now it becomes again even more clear. What this means, when there is 1 unit, when 1 million increase in our GDP, the GDP of Pakistan, then on average there is 0.75 million increase in the taxes. Now just come it and take it again, and this is the tax, and this is beta 1 hat plus again I would like to 0.75x GDP, and I say that it is in billion. This is also in this is billion, this is billion. It has no meaning. I can't say that it is billion because now it is not a variable. So what is this here? Beta 2 hat is here. Now look at this, the same equation, now the def interpretation has become changed. Now what I am saying, that if the GDP of Pakistan changes by this billion, 1 billion, in previous case here I was saying 1 million. If the GDP of Pakistan increases by 1 billion rupees, $1 billion, there is 0.7% increase in our taxes on average, 0.75 billion taxes on average. So what is the conclusion and what is the inference from here? That although in the practicality there is no difference what we are using the scale for the same study, but still they are the meaning changing, the interpretation changing, and you are, I think you should take care of this and you will enjoy this situation. And what are the scaling factor here? I have given it the name W's. So W means, for example, this is if your y is equal to W1, you take a new variable y star. What you do? You multiply it your y, and if it is I, it is also I. So what this says, that you have generated a new variable and it is equal the multiplication of W1I. Now this is a constant, it is a known constant, it may be 100,000 million billion, and you are multiplying this constant with all the values of the yi. If I like to draw here, this is for example y, these are y values, these are 3, 6, 9, and I say that I want to generate a new variable y star from here, and y star is equal to 3y. Now I have replaced the W with this 3. So what will be this? This will be 9, this will be 18, and this will be 27. So this is the meaning of the W's here. So I will be explaining. These are the not W's of the Wasim Akram and Waqar Yunus that that was a huge threat for the batsmen in the late 90s. Now what is the relationship if you measure the change scales and this, what are the formula? There is a change. Look at first that how you have generated this series, and now your new variable is y star is equal to W1yi. If you look at here, I have showed you by generating this. We may use it on the e-views and you may enjoy this. So what is this? If this is the case and we assume that the x, we have also generated a new variable xi. This is the yi star, and you have W1, a constant, known constant, 100, 200, million, billion, and it could be only 2. W1 yi and the other is xi star is equal to W2 xi. What this means? The first constant, the W you call it W1, and this is the W2. So what this means, definitely now the parameter you will estimate, in this case all the parameter you will mention it by star, and in this case you will show it by hat. So if you look at the here, if you apply OLS method, ordinary least square, look at there is no difference in the formula. Beta 1 hat is calculated in the same way as beta 1 star had been calculated. Similar formula for this, only the variable is changed. Here you are taking the y bar, here you are taking the y bar of y star variable, that is your new variable. Here x bar is here x star bar, and here beta 2 hat, and it is here beta 2 hat star. If you look at the, now here, this is the situation, no difference, only what is this, in one side you are getting the formula from the variable that you have created new one, this is the y star, that is the x star, and you are using the estimate as the star. So similarly beta 1 hat, look at the set, not a very small difference, the formulas almost identical. The only difference between this is that in the when there is standard variable, or you can say when there is, you have generated a variable and you denoted it by this yi star, so this is now you are using all the variable with the star. So this is the same situation, this is again, and this is again. From this, some are very interesting relationship. What this means, that beta 2 hat, look at this, beta 2 hat star is equal to the ratio of your now w's, the constant on the scale, w1 over w2 multiplied by beta 2 hat. I suppose I would like to give some of the numerical example. Suppose we have 3 known, there are 4 unknown, we say that we know the values of 3. We suppose that the scaling factor W1 was equal to 10, W2 was equal to 5, and we found that beta 2 is equal to 0.10. We suppose all these values. So if I would like to draw this, that without running the regression again, for example, if what I am asking the other regression, first you will run this regression, y is equal to beta 1 hat plus beta 2 hat x, you have estimated this regression. So if you multiply all the values with w1 of y and w2 values of constant with x, you need not to again run the whole regression. yi star is equal to estimate beta 1 hat star plus beta 2 hat star. There is simple link, you have already known the value of this, this and this. Now you can simply say that the beta star hat should be w1 over w2 10 over 5, and it is multiplied by 0.10. So if we solve this, this will become this, if you solve this, this will here 2, and this is 100 by 500, and it will be 1 over 5, and it is simply 0.25. 0.2 rather than 0.25, it is 0.2. So what is the message of this? Kindly, and I will suggest that you should know these the relationship between the variables, between the parameters, because going again back and multiplying each of the value with x, generating new series, similarly multiplying each value of y, generating new series, again running the regression, then getting the beta 2 hat and beta 1 hat. You should, if you have w1, definitely you have the values of w1, w2 you have the value, and you have also the value of beta 2 hat that you have estimated from the first regression. So you need not to go back, immediately apply this formula and get your required result for the beta 2 hat star. So if I think here is even more simple relationship, for example, I would like to say that we suppose that beta 1 hat is equal to 10. Now what this means, now immediately I can show that beta 1 star hat is equal to, look at this, w1, you have this value of w1, this is 10, and multiplied by beta 1 hat, you have just supposed that this is 10, and beta 1 star hat, it will be equal to 100. So in this way, much of your exercise, effort, time is saved, and you immediately directly. And I think you can reverse these equalities. For example, if you want to see the value of beta 2 hat and you are given the values of W1, W2, beta 2, I will be just reversing this, and I will like to leave all others on your responsibility to do this. For example, if someone gives me the values of, someone gives me that beta 2 hat star is equal to 0.20, and the other he says that W1 is equal to, we suppose that it was equal to 10, and W2 is equal to 5. So what this means now, rather than asking beta 2 hat star finding 2 star hat, so he asked me to find beta 2 hat. Now we know the formula that beta 2 star is equal to W1 over W2 multiplied by beta 2 hat. So what will we do? Now we have to find the values of beta 2 hat from here. So what we will be do, beta 2 hat, immediately the formula will become beta 2 hat star and multiplied by W2 over W1. This is multiplying, on other side it will be divided and it will become reverse. So now you can find if beta 2 star is equal to 0.2 or 20, and W2 is now 5 over 10, and it will be equal to beta 2 hat. So what this means, beta 2 hat now is equal to what you can say that this is 10 by 100. The above equation become 10 by 100, and this is 0.1. So the value of beta 2 hat is now 0.1, and you need not to run the regression. It was indirect relationship, and you immediately capture this. So I was talking about the relationship between the beta stars and beta hats. So if you remember, we were in the discussion of variance of beta 1 hat, and I said that I will be completing it, that variance of beta 1 hat is equal to W1 square variance of beta 1 hat. Just let me see that this is variance and this is star. This is definitely star. So if I assume the value of variance of beta 1 hat, I say that the variance of beta 1 hat is equal to 5. This is the supposed value. So W1 we know, so the variance of beta 1 star hat will be equal to W1, you know, that is the 10, and this is square, and it is multiplied by 5. So variance of beta 1 hat star will equal to 100 multiplied by 5 is equal to 500. So this was the relationship between beta 1 hat, variance of beta 1 star, and the variance of beta 1 hat. And I am sure you can do it from far if you want to see that the variance of beta 1 hat. Here we were interested in variance of beta 1 star hat. Here we are interested only variance beta 1 hat. So what will be this? This W I will go on that side, and it will divide, and it will become 1 over W1 square, and it is with variance of beta 2 hat. So this is the situation in here, that what is the, when we know, remember such kind of formula, a lot of our effort, a lot of our time is saved. So look at this, for example, X, this is the Y. If this is, for example, 3, 7, 8, 9, and it is 1, 4, 6, 10, and you run the regression, you say that Y is equal to beta 1 plus beta 2x. So what this means, you come with that the Y hat is equal to beta, this is, I am just supposing, beta 1 is equal to 5 plus this is 0.6x. This is now beta 2 hat. Now immediately someone asks you, he immediately tells you that the W1 is equal to 10 and W2 is equal to, you can say, the 2. So what he means that you know that the Y star now will be equal to W1 yi and X star new variable I will be equal to W2 xi. So what this means, you have to now generate a new variable xi here, and that is the xi star. And look at this, xi star is equal to W2 into xi. W2 is equal to here 2, so I would have to multiply each value. This will become 6, 14, 16 and 19. Similarly, I will have to generate a new variable, that is the y star here. And what we will say, the y star W1 is equal to 10 and y star is equal to W1 yi. So this is 10, this is 40, this is 60 and this is 100. So now I will have to again run the regression. Y star is equal to beta 1 star plus beta 2 star x. It will take time, but immediately if I know the relationship between these formulas, you can see from here, now immediately I can find the value of beta 2 star. I need not to go do this all exercise that I will be generating new variable and then I will be regressing this. This will eat up most of our time. So if you should remember this, you should have been very tricky and you should remember the formulas, because if you are given any of the value beta 2 star or beta 1 star, then you will have to be able to capture or you calculate the values, and it is very simple. And even sometimes if W1 and W2 are very small, then even you can just one bird's eye view, you can say that this is the situation. The one most interesting thing I am going to explain, that the R square is showing all its previous properties. That what we said, that it is symmetric and it is independent of scale and origin. Look at here, whatever the situation you generate the variable, this is that R square xy, and with the coefficient of determination with the new generated variable is the same. For example, if you look at here, here from in this and this R square xy, I suppose this is 0.9. And come here, if I say that between this, that is now R square between x star and y star, it should be equal to also 0.9. So we will be proving it on e-views. So I think it is time to the falling of the curtain, and I would have to give a brief and quick summary to you for this. So what is the summary? Summary is that we started from today a bit new kind of regression, and that was the regression through the origin. It is a simple, the difference between the traditional, or you can say the regression we kept on studying previously, that the difference between in these two is that in the first one we use intercept and in the other we do not use intercept. So what this means, it brings some new scenario before us, and the scenario is very interesting. The scenario says that now there is a direct relationship between the dependent and the independent variable. There are theories that shows that there is a relationship and direct relationship. For example, I gave you a very interesting example that when the state bank increases the money supply, it doubles the money supply. On the other hand, the theory says that the classical theory of monetary, the quantitative theory of money says that the prices go up. And I think go in the same way. If you double the money supply, the prices will double. If you half the money supply, the prices will become also half. And I think nowadays you are going through this phenomenon that is a very bitter phenomena. Every day you are listening that the State Bank of Pakistan is pumping currency to the market, and at the same time you are going going to the shops and markets and you are looking that this is the inflation is increasing. So this is the regression through the origin. Should we use this regression through the origin? I would suggest that avoid at any cost regression through the origin, but if you have some strong and solid, concrete and discrete knowledge and the theory is so strong, then you can use this regression through the origin. When you use regression through the origin, some of the formulas are changed. I am not going to write these formulas. I would like to just talk about the good measure of goodness of fit, or the you can say the coefficient of determination, or the R square. R square in this means you will say that this, in case of the regression without intercept, regression through the origin, you will say that this is now the raw R square, and the other R square, you know that formula. And the important and the indirect message is here, now these two R square are not comparable. R square is only comparable with its similar R square. Now at one side there is raw R square and the other side there is the conventional R square. So these are not comparable. So this was the property of the regression through the origin. The other was, we discussed about, we derived the formula of beta 2 hat, and why we did not derive the formula of beta 1 hat, because now it is out of the model and the regression is running through the origin. Then we came that what are the value of scale and units. These have the significant values, because if some researcher is using in GDP in billion, the other is using in trillion, and the other is using in billion, million and trillion. So if he is using this kind of, the practicality of the issue remain the same, but the interpretation and some of the formulas and interesting relationship between the formulas emerge, that we learned about this, and I hope you have remembered this. So goodbye and Allah Hafiz.